In this problem, we're going to use the graph of a function in order to answer a variety of questions regarding its graph. For example, the first thing that we want to do is find f of 0 and f of -6. This essentially means that we want to find the y-coordinate on the graph of the function when x is 0. The y-coordinate when x is 0 is 3, therefore f of 0 equals 3. To find f of -6, we want to find the y-coordinate on the graph of the function when x is -6. Because the point on the graph is -6 comma -3, we know that f of -6 equals -3. F of 6 is going to equal 0. F of 11 is going to equal 1. Is f of 3 positive or negative? What we have to do is notice that at x is 3, the y-coordinate is positive, therefore f of 3 is going to be positive. Part D, is f of -4 positive or negative? Once again, find the x-coordinate for at -4, and we can see that the y-coordinate is going to be negative, therefore f of -4 is going to be negative. For what values of x is f of x equal to 0? Put another way, we're asking for what values of x do we have a y-coordinate of 0? Well, that occurs at x is -3, at x is 6, and at x is 10. For what values of x is f of x positive? Here we're looking for the x-coordinates for which the graph is above the x-axis. The graph is above the x-axis between -3 and 6, and it's also above the x-axis for x bigger than -10 and less than or equal to 11. What is the domain of f? To determine the domain of f, we look at all the x-coordinates for which the graph exists. The graph exists for all x-coordinates between -6 and 11. So the domain of x is the set of all x such that x is between -6 and 11 inclusive. Or if you want to use interval notation, -6 to 11 with brackets on the endpoints indicating those points are included. What is the range of f? To determine the range of f, we look to see where the graph exists for all the y-coordinates, or for what y-coordinates the graph exists. The graph exists from a low of -3 to a high of 4, so the range is the set of all y such that y is between -3 and 4, or using interval notation, -3 to 4, again with brackets indicating the endpoints are included. We have a few more questions to answer. Part I asks, what are the x-intercepts? These are the points where the graph crosses or touches the x-axis. The x-intercepts are -3, 6, and 10. The reason I only have to report the values of the x-coordinate is because when I say what are the x-intercepts, it's understood that the y-coordinate is 0. What is the y-intercept? The y-intercept is the point where the graph crosses or touches the y-axis. We can see that the y-intercept is 3. Again, we don't have to report the x-coordinate because it's understood that the x-coordinate is 0 at the y-intercept. How often does the line y equal 1/2 intersect the graph? We can pretend to draw the line y equals 1/2 on the graph. It's going to intersect here, here, and lastly here, so it intersects the graph 3 times. How often does the line x equals 5 intersect the graph? The line x equals 5 is a vertical line. We can see that it's going to only intersect the graph 1 time. So the answer is once. For what values of x does f of x equal 3? Another way of stating this question is, what is the x-coordinate when the y-coordinate is 3? The x-coordinate when the y-coordinate is 3 is either 0 or 4. So the values of x such that f of x equals 3 are 0 and 4. For what values of x does f of x equal negative 2? Another way of asking this question is, what are the x-coordinates when the y-coordinate's negative 2? The answer is negative 5 or 8. In this next problem, we're going to use the vertical line test to determine whether the graph of a relation is a function. In this particular graph, you can see that any vertical line that I draw intersects the graph of the relation in at most one place. Therefore, this graph is that of a function. Because this graph represents a function, we have some additional information that we want to figure out. In part A, we want to know the domain and range of the function. The domain of the function is the set of all x-coordinates for which the graph exists. We can see that the graph of the function exists for the set of all x such that x is between negative pi and pi inclusive. If you're a fan of interval notation, we would write the domain using brackets with the endpoints negative pi and pi. To find the range of the function, we look for the set of all y-coordinates for which the graph exists. We can see that this graph exists for the set of all y such that y is between negative 1 and 1 inclusive, or using interval notation, negative 1 to 1, again with brackets because the endpoints are included in the range. In part B, we want to identify the intercepts of the graph of the function. The x-intercepts are the points where the graph crosses or touches the x-axis. We can see that the graph crosses the x-axis at negative pi over 2, and it also crosses at pi over 2. The y-intercept is the point where the graph crosses or touches the y-axis. We can see that the graph crosses the y-axis at 1, and therefore the y-intercept is 1. Part C asks us to determine if any kind of symmetry exists in the graph. We can see from the graph that we have y-axis symmetry because if I took the portion of the graph for which x is bigger than 0 and folded it over the y-axis, it would land on top of the portion of the graph that exists for x less than 0. Therefore, the graph of the function has y-axis symmetry.